Welcome to BUSN3430 Operations Management. This is Week 3, Lecture 2. Today, we are going to talk about process flow diagrams and key metrics. Here is the roadmap. First, we will learn to see a process by drawing it. Then we will define the 3 key metrics that describe any process. After that, we will meet Little's Law, the relationship that ties those metrics together. We will work through 2 solved examples, one in a clinic and one in a retail store. Finally, we will find the bottleneck, the step that limits everything else. By the end, you will have a simple toolkit for diagnosing almost any operation. Get a pen and paper ready. You will want to work the examples along with me. Before we dive in, let's be clear about where we are headed. These are the goals for the lecture. You will be able to draw and read a process flow diagram for a simple operation. You will be able to define and calculate 3 metrics: inventory, flow rate, and flow time. You will apply Little's Law to connect them. You will identify the bottleneck in a process. And you will explain why any of this matters to business performance. Notice the question at the bottom of the screen. If you cannot measure a process, how can you improve it? That question is the spine of the whole lecture. Measurement is not paperwork. It is the thing that turns a vague complaint about slowness into a specific, fixable problem. So let's start with seeing. Look at the photograph on the screen. It is an ordinary coffee shop in Brooklyn. One customer is ordering. Another is receiving a drink. One is walking out and one is walking in. That is a process, captured in a single frame. A process flow diagram is just a map of that motion. It shows how flow units, which might be customers, orders, materials, or patients, move through steps from input to output. Think about the last coffee you bought. You joined a line, you ordered and paid, you waited, you picked up your drink. Each of those is a step in the diagram, and the arrows show the sequence. Drawing this is always the first move in process analysis, because you cannot improve what you cannot see. Now let's turn that coffee shop into an actual diagram. Follow the boxes across the top of the screen. Customer arrives, join queue, place order and pay, wait for drink. Then the flow turns down and back. The barista prepares the drink and the customer picks it up. Our flow unit here is one customer order. Below the diagram, you will see the 5 elements every diagram needs. Flow units, what moves. Activities, what happens. Buffers or cues, where things wait. Arrows, the direction of flow. And clear start and end points. Pay special attention to the cues. Waiting adds no value for the customer, but it consumes time and it costs money. That is why the diagram is so useful. It shows you exactly where the waste is hiding. With the picture drawn, we can start to measure it. Cashon and Terviesch describe any process using 3 metrics shown on screen. The first is inventory. That is the number of flow units inside the process right now. In our coffee shop, it is the customers who have ordered but not yet received a drink. The second is flow rate, sometimes called throughput. That is how many units finish per unit of time, say customers serve per hour. The third is flow time. That is how long one unit takes to travel the whole process, from joining the line to walking out with coffee. Inventory, flow rate, flow time. 3 simple counts. And they are linked by one of the most elegant relationships in operations management, which is exactly where we are going next. That relationship is Little's Law, and it is on the screen in front of you. Inventory equals flow rate multiplied by flow time. I equals R times T. John Little proved it mathematically in 1961. 2 things make it remarkable. First, it is universal. It holds for any stable process in any industry anywhere. A coffee shop, an emergency room, a factory line, a bank branch. Second, it is practical. If you know any two of the three metrics, you can compute the third. Know how many customers are in the system and how fast you serve them, and you know how long they wait. Know the wait and the crowd, and you know your throughput. Treat this not as a formula to memorize, but as a diagnostic tool you can use on a real operation. Let's put the law to work. Our first example is the Flatbush Medical Clinic. Look at the problem panel on the left. On a typical morning, 18 patients are in the clinic at any moment, and the clinic completes 6 visits per hour. Question A asks for flow time. Follow the middle column. Little's law rearranged gives T equals I divided by R. 18 divided by 6 is 3 hours. So the average patient spends 3 hours in the clinic. Now question B. Management wants that down to 2 hours, with inventory unchanged. R equals 18 divided by 2, which is 9 patients per hour. Look at what that means. Cutting patient time by about a third demands a 50% jump in throughput. Little's law just turned a patient experience goal into a hard operational target. Our second example moves from healthcare to retail, and it delivers a surprise. On the left, a Brooklyn boutique on a busy Saturday. 12 customers browsing at any time, each staying 24 minutes. Watch the unit conversion in the middle column, because this is where students lose points. 24 minutes is 0.4 hours, so R equals 12 divided by 0.4, which is 30 customers per hour. Now the store runs a promotion and browsing time rises to 36 minutes, or 0.6 hours. The flow rate falls to 20 customers per hour, a drop of about a third. The store is just as full, but it serves fewer people. That is the trade-off in the box on the right. Bigger baskets, fewer customers. Little's law makes that tension visible and quantifiable. So far we have measured the process as a whole. Now let's find the step that controls it. On screen is the bottleneck concept. Every step in a process has a capacity, a maximum number of units it can handle per hour. The bottleneck is simply the step with the lowest capacity. It is the weakest link. Here is the critical insight. The flow rate of the entire process can never exceed the capacity of the bottleneck. Speed elsewhere does not help. If the prep station handles only 30 orders per hour, the restaurant serves only 30 orders per hour, even if every other station could do 50. We will go deeper into capacity analysis later in the course. For now, remember this. Finding the bottleneck is the highest leverage move in process improvement. Let's bring every idea together in one scenario. Behind the numbers, you can see Brooklyn Bite, a food truck working the lunch rush on a busy street. Read down the list of 4 steps and their capacities. Order taking, 60 orders per hour. Food preparation, 40. Assembly and plating, 55. Payment and handoff, 70. The lowest number is 40, so food preparation is the bottleneck, and it sets the flow rate of the whole truck at 40 orders per hour. Now apply Little's law. If 20 orders are in the system, flow time equals 20 divided by 40, which is 0.5 hours, or 30 minutes per order. So here is the management question. If you can add 1 worker, where do they go? Food preparation. Capacity added anywhere else changes nothing. Let's pull it all together. 5 takeaways are on the screen. 1. A process flow diagram maps how units move through steps, making the invisible visible. 2. The 3 key metrics are inventory, flow rate, and flow time. 3. Little's law says inventory equals flow rate times flow time, so knowing any two gives you the third. 4. The bottleneck is the step with the lowest capacity, and it sets the flow rate for the entire process. 5. If you can draw it, measure it, and find the bottleneck, you can improve it. Next lecture, we move from diagnosis to treatment. We will study the 3 levers of process improvement and apply them to real business scenarios. Bring your diagrams from today. We will build directly on them. See you then.